Hi folks, so now we're going to start our go over the introductory section of chapter 12 on continuous latent variables. So let's get into it. Okay, so it says we're now going to explore models in which some or all of the latent variables are continuous. Okay, and so why should we do this? So many data sets have the property that data points all lie close to a manifold of much lower dimensionality than that of the original data space. Your data is going to be arriving in 100 dimensions, but turns out the underlying manifold that's generating is maybe 2 or 3 dimensions. So you want to be able to uncover that. To see why this might arise, consider an artificial data set constructed by taking one of the offline digits, represented by a 64 by 64 pixel gray level. So let's just imagine one of these guys, basically. Let's say embedding it in a larger image, a size of 100 by 100 by padding pixels, and then in which the location and orientation of the digit is varied at random, as illustrated in figure 2.12.1. So we're going to generate this thing and then just move it around, and just like it might happen where from real digits, right? Maybe the paper was rotated, the camera wasn't quite aligned, things like this. Okay, so each of the resulting images is represented by a point in a 100 by 100, so a 10,000 dimensional space, right? So each, we have flatten all the pixels and you've got 10,000 dimensions. However, across the data set of such images, there are only 3 degrees of freedom. Okay, so you've got your 10,000 dimensional observations, but there's only 3 degrees of actual variation in it. So you really want to be able to capture that. Corresponding to vertical and horizontal translations and rotations. The data points will therefore live on a subspace of the data space. So I think it doesn't mean subspace in kind of necessarily the vector space sense, but just a kind of a subset whose intrinsic dimensionality is 3. So you have some data that's kind of being embedded. So here's an example of that. So here is our manifold of data, and it's living in a 2-dimensional space. It's embedded in a 2-dimensional space, but intrinsically it's 1-dimensional. And that's kind of what that notion is about. Okay. Now the manifold will be nonlinear because, for instance, and I thought this was a cool example of him showing that, if we translate the digit past a particular pixel, so looking at the value of a particular dimension, looking at the value of the manifold along a particular dimension, that pixel value will go from 0, white, to 1, black, and then back to 0. So essentially what he's saying is, suppose we cared about, let me color it in red. So suppose we cared about that particular position. So that's going to be 1 coordinate along our manifold. And now suppose that the next thing we do, as in generating this data set, is to just move the 3 up and down. Well, you'll see that the value of that pixel will, as you're moving, let's say, along the vertical direction, you will get, the value of the pixel might go like this as you kind of hit all the bumps. And so if it was a linear manifold, you would expect things to move linearly in one direction or another, or stay flat, but that's not what's happening. So you can just kind of see that this manifold that you're going to be living on, that you've embedded, is actually going to be a nonlinear manifold. So I thought that was a nice way of demonstrating that. In this example, the translation and rotation parameters are latent variables because we observe only the image vectors and are not told which values of the translation or rotation variables were used to create them. So that's latent. It just means hidden. That's all it means. So, and they're hidden because we don't know. We just get the digits. We don't know the translation. Okay. For real. Yeah. And he says, okay, there's other degrees of freedom, for example, due to different people's writing styles, but the number of such degrees of freedom will be very small compared to the dimensionality of the data set. Then he talks about another example from the oil data that he's worked with. The data points will not be confined precisely to a smooth low-dimensional manifold, and we can interpret the departure of data points from the manifold as noise. So that's kind of the big idea. This leads naturally to a generative view, which is big these days, of such models in which we first select the point within the manifold according to some latent variable distribution. So maybe we'll try to select points randomly or whatever it is, and then generate an observed data point by adding noise drawn from some conditional distribution of the data. So the idea is, let's see how much of this you can see, but yeah, the idea is, and we'll see this in I think it's section 12.2, but the idea is you sample z from your hidden variable and then you from some distribution, some prior distribution maybe you have, and then you say, well, what are my observations? Well, the observations are going to be coming from some conditional distribution on that z. So that's kind of your generative model for how your data was produced. The simplest continuous latent variable model assumes Gaussian distributions for both the latent, so this is going to be Gaussian, and observed variables. So this will be Gaussian as well. This conditional distribution will be Gaussian. And makes use of a linear Gaussian dependence of the observed variables on the state of the latent variables. This leads to a probabilistic formulation, which we're going to talk about a lot, of the well-known technique of principal components analysis, as well as to a related model called factor analysis. Okay, and we'll get to all of that. So what we're going to start with is a standard non-probabilistic treatment of PCA. So we're going to derive it kind of the way that it was originally derived, and then we'll see how and then later on we're going to show that it arises naturally as a maximum likelihood solution to a particular form of linear Gaussian latent variable model. And then this is going to be viewing things from that perspective. It's going to bring lots of advantages, which we'll discuss. And then later on, we're going to generalize this to beyond the linear Gaussian assumption and talking about things like independent component analysis, kernel PCA, nonlinear autoencoders, etc. Okay, but the first chunk that we're going to talk about is going to be about PCA and deriving it the way, kind of one of the ways it was originally derived. So that was the introduction, and I hope you'll join me in the next section when we're going to start our discussion with PCA. See you then.